Good morning everyone. Today's class is related to the unit number 2 in digital electronics, in which we are going to learn about combinational circuits. The combinational circuits means the circuits where we are going to have adders, decoders, encoders, mux and demux. Let's get on to each and everything. Like first let's understand what is exactly the combinational circuit. Now, what exactly the combination circuit and combination circuits, how does it look, will let us see. Now, for example, if I am having a block which is called as combinational circuit can be anything, combinational circuit, for which I am providing an input and I am also providing one output. Means the circuit should contain one input and one output should be there, and it should not contain any kind of feedback paths. Means for a perfect definition, I can call a combinational circuit as a circuit without a feedback path is called as combinational circuit. Now examples of combinational circuits. Now what examples I can have? I can have adders. Now adders is of two types, like off adder. I can have full adder. After adders I can have encoders. I can have decoders. After that we have multiplexers. Then demux or demultiplexer we call it as. So these all circuits come under combinational circuits. We'll see each circuit in detail in the next slides. Now, adders. In adders, we are having two things. One is off adder, the other one is full adder. Let us see how does an off adder look like. Off adder means I am going to have a circuit which is going to add 2 bits of information. For example, if I am having A as one input, B as the other input, and as you know that adder has one pure application of generating sum and carry. Now if I am considering two things, A and B as my inputs, and outputs will be generated as sum as well as carry. For example, as it is two inputs, we are going to have the number of combinations as 4 combinations we are going to have. Options, let's wait for the slide. A and B as my input values, output as sum and carry. Now 2 inputs means the number of combinations that I can get is 4 combinations. So 0 0, 0 1, 1 0, 1 1 as my 4 combinations. Now for some value to get generated. Now I am talking about purely about off adder. Means I am just adding 2 bits of information here. So 0 0, sum gives me 0, carry gives me 0. For 0 1, sum is 1, carry is 0. For 1 0, sum is 1, carry is 0. For 1 plus 1, sum is 0, carry is 1. So this is what the information related to the off adder. Now for this off adder, I need to have a Boolean expression. Now Boolean expression can be represented for sum. Why? Because these two are my outputs. So I need to represent expression for my sum value as well as expression for my carry. Now sum value is 1 at this particular point, sum is 1 at this particular point. Means S is equal to 1 at A dash and B. A dash B plus 1 it is present at A B dash. A B dash. So if you observe clearly the expression is of A exclusive B operation. Means so I am going to get some value when I am performing a exclusive OR operation between A and B. Now coming to carry. I am having 1 at only at one point of view where A value is 1, B value is 1, where I am generating carry. So at that particular time, the carry equation becomes is equal to A. Now these are my Boolean expressions. Now coming to my logical diagram. So logic diagram can be represented like this. The first one is A exclusive with B operation. Means I should have XOR operation performed between A and B. So A and B exclusive OR operation is giving me some value. Next expression, my carry equation. So I need to generate a carry, that is AND operation between A and B. Means I should take A terminal, I should take B terminal, perform a AND operation between them to get a carry value. So this is the logic diagram. So for off adder, we need to draw functionality table, we need to draw Boolean expressions, and also we need to draw logical diagram. So this is the operation of off adder. Let's get on to full adder. Now this is off adder where we got operation to perform sum between only 2 bits. Now when we are having more than 2 bits, that is if we are adding 3 bits, how the adder is going to look like? Well, let us see in it. Now let us get on to full adder. Full adder means I am having input bits as A, B, C as inputs. I am having sum and as well as carry as my outputs. So I need to perform addition operation between A, B, C as inputs, sum and carry as my outputs. Now let us draw the functionality table first. Functionality table for my full adder. So A, B, C as my inputs first. Next, outputs as sum and carry. So for 3 bit of information as inputs, the number of combination for 3 bits will be 2 power 3 is equal to 8. So 8 combinations I need to get here. So those 8 combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So you got totally 8 combinations. Now I need to write both sum value as well as carry value here. Now the sum will be 0 and carry 0 for 0 combination. For 1, sum is 1, carry is 0. For 0, 1, 0, sum is 1, carry is 0. For 0, 1, 1, sum is 0, carry is 1. For 1, 0, 0, sum is 1, carry is 0. For 1, 0, 1, sum will be 0, carry will be 1. Why? Because 1 plus 0 is 1, 1 plus 1 is 0. So sum is 0, carry is 0. Next, this is going to give me sum 0, carry 1. Next here, 1 plus 1 is 0, 0 plus 1 is 1 with carry 1. So I have got my functionality table for my full adder. Now coming to Boolean expression. For my full adder. Now if you observe, the sum values are 1 at this particular point, 2, 3 and 4. So 1, 2, 3, 4 are the values which is going to give me sum as 1 value. So let us represent all those values. Sum is equal to what it is? A bar, B bar, C. Means A bar, B bar, C. Next, this has A bar, B, C bar. Next, this has A, B bar, C bar. Next, the last one, the last combination is giving me A, B, C. There is no bar here, only A, B, C. So the sum, we got this particular expression, right? Now similarly, now this expression can also be written as, when we simplify using Boolean laws, or if we use a Carnot map to resolve this equation, we are going to get expression as A exclusive B exclusive C. So this is what the simplified expression for our sum value. Now coming for carry, the carry expression can also be represented from the functionality table. The carry is 1 at this particular point, 1 at this point, 1 at this point, 1 at this point. Now at that particular point my values are A bar BC, 1 at this particular point, A B bar C. Now at this point A B C bar, A B C bar, and the last one as A B C. Now when you simplify using Boolean laws or Carnot map, you get this particular expression as AB plus BC plus CA. So this is what the simplified expressions as Boolean expressions for our full adder. Let us see the logic diagram. Logic diagram. Now, sum expression. Exclusive OR operation between A, B, C means I should have 3 terminals. An exclusive OR operation which is producing me some value. This is XOR gate, which is going to give with inputs A, B, C, which is going to give me some value. That is some expression I got as a logic diagram. Now I need to represent carry value. So carry can be represented as, so A, B, one AND gate. Next BC. So B and C, one more AND gate. The last one C. C and A terminal. I am taking one more line. Draw an AND gate. So I have got 3 AND gates, A, B, B, C, C. Now let us add them with an OR gate, producing output as carry. So this line will give me AB, this is going to give me BC, this is going to give me C. So this is how the logic diagram looks for a full adder. These are the 2 combinations or 2 circuits in a combinational circuits where we are going to tell how a adder is going to work for both half adder as well as full adder. Now these 2 applications are very important for us. Now apart from this half adder and full adder also we have some other adders. Now if you observe clearly, and now whenever I am having adders like, if I am having adders like this, if I am having a full adder, like I am taking a cascaded structure. For example, if I am taking a 4-bit should be added with the other 4-bit. Like for example, if I am having A1, A2, A3, A4 should be added with B1, B2, B3, B4, which is giving me S4, S3, S2, S1. Now, whenever S4 is generated, I might have a chance of generating C3, right? I might have a chance of generating C2. I might have generating chance of C1. So I might also have a C0. C0 I am considering permanently as 0. So whenever I am doing an addition operation, 3 bits are getting added to generate a 4-bit sum. So I am taking a 4 full adders. I am taking a 4 full adders, which is called as parallel adder, where I am giving 2 inputs as A0, B0, A1, B1, A2, B2, A3, B3, which are generating me S0, S1, S2, S3. This combination might give me C0, or this can give me C1, this can give me C2, this can give me C3, this can also give me C4, right? Some other can. but I am fixing my thing C0 permanent. So these particular combinations or these particular kind of additions I call as parallel addition. Parallel addition or parallel adder we call, or cascaded full adders I can call. So these combinations we use to add a 4-bit number. If it is a n-bit number, I require n full adders to generate my sum value as well as carry value.